Welcome to another lecture by your teacher Desmond. Today we are covering rational functions. So this is the general form of a rational function. The general form of a rational function is this: f of x equals p of x over q of x. And p of x and q of x are polynomial functions, and q of x is forbidden to equal to 0. You'll see why in a second. So these are the graphs of rational functions. The parent function of rational functions is f of x equals to 1 over x. And these are the graphs. So f of x equals 1 over x is a hyperbola. F of x equals negative 1 over x, the inverse, is also a hyperbola. So the domain and range of rational numbers, so the actual domain and range cannot equal to 0, obviously. This is an example of how to find domain and range. So denominator, we take it out, equal it to 0, we find 2 over 3. So the domain would be x. Real numbers, x cannot equal 2 over 3. To find range, we switch out x and y. Find for denominator again. Equals 0, y equals 2 over 3, and range is y, element of R. Real numbers, y cannot equal to 0. So for intercepts, we have this function. So to find y, we f of x, for x plus 1 equals 0 and x equals negative 1 over 4. So x-intercept will be negative 1 over 4 to 0, and the y-intercept of this will be 0 and 1. Plus 1. Zeros of a function. The zeros of a rational function are the values of x that make numerator of a function equal to 0. In other words, they are the values of x that makes fx equal 0. Oh my god. Just seeing how fx can be 0, we have to look at the example. So first off, we would factorize the top, and it will be this. We can cancel out these two, and the end product will be f of x equals x plus 2, and that will be the values that make it 0, so it's the 0 of the function. These are the discontinuities. Wholes only exist when numerators and denominators have linear common factors. For example, f of x equals x squared plus 5x plus 6 over x squared plus x minus 2. To find the common factors, we first factorize it, and we cancel out x plus 2, and we get x plus 3 over x plus 1. So once we get that, we can put that into the factoring. We take x minus 2, we put it in, we get negative 1 over 3. So the x will be negative 2, and the end product y will be negative 1 over 3. And this is the whole, the coordinates of the whole. So restrictions in a rational function, any excluded value in any x value that makes the function y value undefined. These values should be excluded from the domain of the function. So for example, the restriction value of function y equals 2 over x plus 3, the restriction would definitely be x equals negative 3, because when x is equal negative 3, the value of y is undefined. So the domain of all numbers is except x over 3. Yeah, this is basically why it can't equal to 0, because when x over 3 is plugged into it, it equals to 0. Identify and determine the restrictions in the domain. To identify the restrictions in the domain of a rational function, we need to look at the denominator of the function q of x and determine the values that make x and the values of x and make it equal to 0. These values are called vertical asymptotes. Wow, interesting. And are not in the domain of the function. For example, let's try to find the vertical asymptote. F of x equals x squared minus 4 over x minus 2. The denominator of this function is x minus 2. This function is defined when x is equals to undefined, because as you can see from the last, because it equals to 0. So x equals 2 is undefined, making this function undefined. So since division by 0 is not allowed, therefore the restriction x equals 2 is actually also the vertical asymptote and the domain of the function is all real numbers except for x equals 2. So yes, that's how you identify and determine the restriction. So these are the type of asymptotes. Asymptotes are the line where it never, ever touches. For example, in parent function y over x, both x and y axis are asymptotes. If I can show you the graph again, right here, x and y axis, they never touch it. They get really, really close. Maybe sometimes in graphs they touch it, but they never, they get, maybe sometimes they get really, really close to it, but they actually never touch it. So yes, so both x and y axis are asymptotes of parent function. And for a rational function in the form of y equals a over x minus b plus c, the version asymptote excluded at the end is x equals b, and a horizontal asymptote at y equals c, x minus equals b, right here. Determine the equation of asymptotes. So for example, x squared minus 4 over x minus 2. The denominator is x minus 2, which equals 0 when x equals 2. Therefore, the equation of the vertical asymptote is x equals 2. Great. So for horizontal asymptotes, if the leading coefficient are equal, these are the three rules basically. If the leading coefficient is equal, the equation of the horizontal asymptote is y equals. So you gotta ratio it. Leading coefficient of numerator over leading coefficient of denominator. So since these are not equal, but if it was equal 2 and 2, it would be 1 and 1 x. So 1 over 1 is 1. So horizontal asymptote would be 1. If the degree of the numerator is less than the degree of the denominator, the horizontal asymptote is y equals 0. So it's exactly y equals 0. Great. If the degree of the numerator is greater than the degree of the denominator, there is no horizontal asymptote. Straight up. So the end behavior of rational function, let's consider this. There are three different end behaviors. See? So for this one, this function, the degree of the numerator is 2. The degree of the denominator is 3. So the function, straight up, has a horizontal asymptote of 0. Because the numerator is less than the denominator. So as x approaches positive or negative infinity, the function gets closer to the horizontal asymptote, but never touches it. So you can imagine, right? So if the degree of the numerator is equal to the degree of the denominator, the function has x. Yeah, so that's it. That's the end behavior. You kind of imagine it, because once you have the idea of where the horizontal asymptote is, you can imagine it's like from either positive or negative. That's only that much. So for this, the leading coefficient is like 2 and 3, but degree is same, so you gotta ratio it. So 2 over 3, and as x approaches negative infinity of the function, it never touches the y equals 2 over 3, which is the horizontal asymptote. It never touches it. It gets close to it, but never touches it. If the degree of the numerator is greater than the degree of the denominator, the function has no horizontal. Yep. Yeah. So if there's no horizontal asymptote, there would be the function would decrease or increase without bound as x approaches positive or negative infinity, and it depends on the sign of the leading coefficient. Yeah. For this last one, end behavior, so the degree is 4 on numerator, and denominator is degree 2. So therefore, the function has no horizontal asymptote. So again, as x approaches positive or negative infinity, the function increases or decreases without bound, which depends on the leading coefficient of the highest degree term, which is this positive. Positive and negative intervals. To determine the positive and negative intervals of a rational function, we need to find the zeros of the numerator and denominator polynomials. These zeros represent the points where the function changes sign. If the numerator polynomial has a 0 at a point x equals a, then the function may change sign at x equals a. To determine if this does, because 0 is the flat point, the 0 point, we need to evaluate the function at a point so close to a on either side. If the function output is positive on one side and negative on one side, then there is a sign change at x of a because it's coming in from positive on one side and negative on the other side. Vice versa, if the denominator polynomial has a 0 at point x over b, then the sign may change at x over b, so you gotta find that out. Once we identify all the possible points of change, we can divide the number lines into intervals and test each point to determine the sign of function on that interval. If the function is positive on that interval, we have to say that it is a positive interval. If the function is negative on an interval, we have to say it's a negative interval. So we can see the change by determining whether it's a negative or positive interval. And thank you for listening to Mr. Desmond. This is me signing out.